okay? Picture this. You're lowering massive multi-ton pieces of steel through pitch black, freezing water, completely relying on the hope that they're going to land exactly where your 3D models said they would. Well, spoiler alert, they almost never do. So how in the world do you connect a multi-billion-dollar subsea oil and gas system when the giant pieces don't perfectly align? That's the high-stakes engineering mystery we're unraveling in today's explainer as we dive into subsea jumpers and how they bridge the gap. Let's dive right into this. The harsh reality of subsea engineering is that the ocean simply doesn't care about your blueprints. When you drop a massive structure, like a manifold or a subsea tree, all the way down to the seafloor, you're constantly fighting dynamic ocean currents, installation tolerances, and just the sheer unpredictability of the deep sea. Because of all that chaos, no two structures land on the seabed exactly where the design drawing said they would. Section 1. The As-Built Gap. Meeting reality on the seabed. When these massive structures finally land on the seabed, they create what engineers call the as-built gap. It's the physical distance and misalignment between where a component was supposed to be on paper and where it actually ended up in reality. And we're talking about connecting fixed, incredibly heavy structures here. You can't just nudge them over a few inches. Enter the hero of today's explainer, the subsea jumper. A jumper is a short connecting pipe section designed specifically to accommodate positional and thermal misalignment between two fixed structures. Its entire job in life is to absorb that unpredictable gap. But here's the catch. It has to do this while handling extreme internal pressures, without putting any damaging stress onto the structures it's connecting, and definitely without becoming the weak link in the entire production chain. These jumpers really are the critical final links in the subsea architecture. They make the ultimate connections from the subsea tree to the manifold, from one manifold to another, or from a manifold to a pipeline end termination, which we call a plet. The largest, most complex subsea components in the world absolutely 100% rely on these relatively short pipe sections to make the final flow line connection possible. Section 2. Garden hose versus tailored suit. The two contenders. When it comes to bridging this gap, engineers basically choose between two very different design philosophies. Think of it like this. On one hand, you have the flexible jumper. It's essentially like a garden hose. If the spigot on your house is an inch or two away from where you thought it was, no big deal, right? The hose just bends smoothly to reach it. But on the other hand, you have the rigid jumper. Made of rigid steel pipe, it is exactly like a high-end tailored suit. It has to be cut and fabricated to a highly specific, exact set of measurements, and it has absolutely zero room to stretch, bend, or forgive. Let's break down how they actually stack up against each other. A flexible jumper is made of a multi-layer composite. We're talking things like a stainless steel internal casing, a thermoplastic sheath to keep the fluid sealed, and helically wound steel armor on the outside. This makes it incredibly versatile and way easier to install in deep water simply because it can absorb those larger positional errors without needing a perfect prefabrication fit. A rigid jumper, though, that's a preformed steel pipe. It demands an exact fit and is incredibly sensitive to even the slightest structural misalignment. So, if you're tracking with me, a really obvious question should be popping into your head right about now. If flexible jumpers are so much easier to install and they effortlessly absorb those inevitable survey errors, why in the world would you ever choose to use a rigid steel jumper? Take a second to think about that. Why would engineers willingly choose the harder, completely unforgiving path? Well, the answer comes down to what we call the HP/HT trap, high pressure and high temperature. The reality of modern oil and gas reservoirs is that the fluids blasting out of the earth can be ridiculously hot and under immense crushing pressure. Flexible pipes, with all those polymer sheaths and composite layers we just talked about, are fundamentally limited by their pressure and temperature ratings. When the conditions get truly extreme, flexible pipes just cannot survive. You are literally forced to use rigid steel. There's a great quote from our engineering sources that hits the nail on the head. You generally can't have maximum flexibility and maximum HP/HT rating in the same jumper design. It is a direct, unavoidable trade-off. You just don't get to trade away pressure containment because you want an easier time during installation. If the reservoir dictates extreme pressure and temperature, rigid steel is your one and only option. Section 3. High-stakes subsea metrology. Measuring the deep. This brings us to one of the most high-pressure phases of subsea engineering. Because rigid jumpers are made of completely unforgiving steel, engineers have to capture the exact as-built distance and angles between the two structures on the seafloor before they can even think about building the pipe. This intense measurement process is called subsea metrology. And the level of precision required here, it's absolutely staggering. We're talking about an accuracy of a few centimeters, or sometimes even less. And remember, this isn't happening in a nice, well-lit laboratory. It's happening across distances spanning tens of meters, basically the length of a large swimming pool, but down in the freezing, pitch-black depths of the ocean, fighting currents and crazy hydrostatic pressure. Which leads us to a completely counterintuitive sequence of events for how this hardware is actually built. Here's a detail most people miss. Jumper selection isn't decided at the design office. With rigid jumpers, the design office doesn't make the final call on the shape. First, you drop the main structures to the seabed. Second, you conduct the metrology to measure that exact as-built gap. Third, you rush those measurements back to an onshore facility to actually weld and fabricate the jumper. And finally, you transport it offshore to lower and connect it. It's really one of the only major subsea component decisions that happens this late into a project. To pull off that centimeter-level accuracy, survey teams have to bust out some incredibly specialized tech. They use taut-line systems, advanced acoustic telemetry that literally bounces sound waves between the hubs, and remotely operated vehicles, or ROVs, to help out. They also mount high-quality inclinometers directly onto the subsea hubs to measure the exact tilt and angle of the connection points. All of this highly sensitive data gets fed straight back to the onshore fabrication yard so they can build that perfect tailored suit. Section 4. Connecting the chain. The cost of getting it wrong. Once that massive rigid jumper is finally fabricated on land, it gets loaded onto a specialized vessel, shipped out to the middle of the ocean, and lowered via crane all the way down to the seabed. But the financial and operational stakes of this specific moment, they literally cannot be overstated. Lowering a huge steel pipe with complex connectors at both ends is a super delicate, high-risk operation. The sources give a very stark warning about this. Ordering a rigid jumper fabrication before the final metrology survey is 100% finished is a disastrous sequencing error. Why? Because any survey inaccuracy becomes a jumper that simply doesn't fit, forcing refabrication and a repeat vessel mobilization. And let me tell you, vessel time costs an absolute fortune. If you lower a steel jumper and the angle is off by just a couple of degrees, it won't lock. You have to haul it all the way back up, take it back to shore, cut it, re-weld it, and pay for that expensive vessel all over again. No pressure, right? So assuming the measurements were perfect and it actually fits, how does it lock into place? Well, there are two main methods. Horizontal tie-ins are generally used in shallower waters. They often use bolted flange joints and rely heavily on ROVs or even divers. But out in deep water, we typically see vertical tie-ins. These rely on inverted U-shaped or M-shaped rigid spools that get lowered straight down onto upward-facing hubs using incredibly heavy, complex collet connectors. Let's look a bit closer at those deep water vertical tie-ins. The jumper has this inverted U or M shape, and at each end sits a mechanical collet connector that weighs several tons. Now, because you're dropping literal tons of steel directly onto a billion-dollar subsea tree, these connectors feature built-in soft landing systems. These brilliant little systems absorb the impact, isolate the jumper from the bobbing motion of the ship way up on the surface, and gently pull the connector and the mating hub together. Once it's finally locked in, metal-to-metal seals ensure that not a single drop of high-pressure fluid escapes into the ocean. It really is an incredible feat of engineering just to connect point A to point B down there. Jumpers are these vital bridges that completely forgive the unpredictability of the ocean floor, all while holding back immense explosive pressure. But at the end of the day, they are just the connectors, which begs the question, what exactly are they connecting to? What lies at the very start of this massive, high-pressure chain? That brings us to the true source. In our next explainer, we're going to explore the primary pressure control devices sitting right on the ocean floor, the subsea wellhead, and the incredibly complex Christmas tree. You definitely won't want to miss how engineers control the raw, explosive power of a reservoir miles beneath the waves. Thanks so much for joining me on this explainer, and keep your curiosity deep.